Welcome to a lesson with Dr. Pal. In this video, we will look at some related rates problems. Okay, suppose that we have a cylinder and its volume is increasing. Okay, and it's increasing because the radius is increasing. We want to know how fast the radius is increasing at a particular moment in time when the volume itself is increasing at a rate of 1 cubic meter per minute. So how many meters is the radius increasing per minute instantaneously at this particular moment in time? We're given some information about this moment in time. We're looking at the moment in time when the radius is a third meter. The radius is not going to be held constant at a third meter. The radius is changing. It's variable. So we're going to keep r as a variable as we move along here. But we are assuming right here that the cylinder itself, the height of it, is constant. Okay, so a constant height, and why do we know that? It just says the radius r as a variable of a cylinder of a height 8 meters is changing. The radius is changing, but the height we're going to assume to be constant because of how it was worded here of cylinder 8. And maybe it should have been specified and worded a little better maybe there. But we are going to assume that that is constant. So we can think, we need to relate. See, we know what dv dt is. It'd be nice if we could relate dv dt to dr dt. The first step is to relate the variables v and r together in a function equivalence equation, thinking of r as a function of time and v as a function of time. So we're going to get an equation that relates two functions, and these functions could be built by adding, subtracting, multiplying functions like v and r together. Okay, so we think, do we have such a relationship between our variables v and r? We know that the area of the base of this cylinder is pi r squared. Then you got to multiply by the height, 8, because height times base is equal to volume. There's our equation, not bad. Now you just need to find the derivative equation. So that relates relates dv dt and dr dt together, and that'll come about via the chain rule as you take a derivative of this side is a function, that side's a function, that we're saying these two functions are the same. So the derivatives better be the same. We can take a derivative of both sides, and we're going to get on this side dv dt is equal to, then think of this 8 times pi as being a constant. Just put it at the front. Really taking the derivative of r squared, thinking of r as a chunk, r of t, so it's a function. So we're going to get 2 times r times dr dt using the chain rule. Okay, so now, we have dv dt is equal to 8 pi times 2r times dr dt. We can plug in dv dt, which is 1. This is our time to plug in, by the way. This is our function equivalence equation. So function equivalence, and this is our derivative equivalence equation. And so once we come here, now we're not taking derivatives anymore of things, and we've used the fact that things are variable. Now we're looking at a particular instant moment in time. This is the time to plug in. So at this particular moment when r is 1/3, we did not plug in 1/3 before we took a derivative. That would have been bad. This side would have been a constant. Nope, wouldn't have worked. Okay, so 1/3, and this is 16 pi times 1/3 dr dt. That's what we're looking for. That's our variable, so just write it in. But we know what dv dt is. It's 1. Great. So now we can just divide both sides by this. Well, dividing by 1/3 is the same thing as multiplying by 3. So you could think of this as being 3 over 16 pi is equal to dr dt. And the units, of course, would be meters per minute. So 3 over 16 pi meters per minute would be how fast the radius is changing at this particular moment in time. All right, so I think what I'll do is actually save the next one for the next video. Thanks for watching.